Hello everyone, and let us start our previous discussion that we were doing about the canonical transformations. Okay, so as we had discussed all about these canonical transformations, that why we do this, why it is helpful in doing the old coordinate to be transformed into the new canonical variables. Like if you remember, the canonical transformation is to transform your old uh, canonical variables that are small qp, and that is you have to transform into the new variable that is capital QP. And when you are transforming this, that you have to preserve the Hamilton equation of motion. That if you remember that this is modified Hamilton equation of motion that is in your old variables small p and q, and this is your Hamiltonian, and these are this is the modified Hamilton principle in the new variable as capital Q and capital P. And then that the transformation, this canonical transformation has to be preserve the form of the Hamilton equations or modified Hamilton principle. Okay, and you know that this transformation is we discussed is just uh, to have some mathematical calculation to make it easier, so that you transform the old variable into the new variable such that your Hamiltonian becomes the cyclic in coordinates. Okay, so that the corresponding momenta is going to be the constant of motion, and then solving that equation is going to be easy. And to that if you transform, so your new canonically transform your old coordinates, this QIPI, into this new coordinate capital QIPI, then your this old Hamiltonian becomes the new Hamiltonian, which depends upon Q and P. These are your new variables. Okay, and along with that you have one time dependent uh, component, that is the time derivative of the component, that is this f, which is, you know, we had discussed, is the generating function for this canonical transformation. And then if you remember, we have some lambda here, multiplicative constant, and for this lambda equal to 1, and we have canonical transformation, and then if lambda is not equal to 1, then you have extended canonical transformations. And then we had calculated these, what are the options for this generating function f, because f can depends upon all these uh, q, p and t, and this new q, p and t variables. So these are going to have this is going to depend upon either combination of all these new and old variables. And then there we have four options. This is type f1, type f2, type f3 and type f4 generating functions. And then corresponding to those generating functions, we had discussed that we have the derivative. For example, this first generating function, which depends upon small q, capital Q and t, and that the corresponding function derivative is pi, and this capital Pi, new Pi momenta, is going to be this and this. So similarly, you have f1, f2, f3 and f4 generating function and the corresponding function derivatives for that. Okay, and we had discussed till now this thing. And for example, if you see that f2 is my f2 is qi, generating function is qi pi, and then corresponding to f2, what we have this function derivative pi. And so if you calculate this is f2 by capital Pi from this, so this becomes qi, and this, if you calculate this becomes, the second derivative becomes pi. So you see that the new old variable and the new variables are equal, and new variable and old variable in momenta. So this is a kind of identity transformation. Okay, so if you have a transformation the type f2, which is going to be qp, this is kind of identity transformation. And then if you have pi qi in f3 type, then this is going to be identity transformation with the negative sign. And then you have a mixed and all these things. So till now we had discussed this, and then moving further, what we going to do is we're going to find the condition for the canonical transformation. That if any transformation is given, or like if you have been given, this is in terms of the q and p, this is the new variables in terms of your old variables q and p, small q and p. So if this is given, yeah, or it is given that you have a q is given in terms of qp and p is given in terms of qp, then this kind of transformation, that how to find that this transformation is going to be canonical or not. Okay, so there are certain conditions which we can apply to directly figure out that whether this transformation is going to be canonical transformation or not. So first thing, if my Hamiltonian function doesn't change in such transformation, then this is going to be the old Hamiltonian is going to be the new Hamiltonian is going to be k. Okay, now taking the time derivative, if this is my this qi is my time given the transformation. So if I'm going to take the time derivative of this function, this qi, so because it depends upon a small q and p, so that is this is basically ddt of qi. So that is what I'm going to have is q dot. So first q depends upon this small q, so this is with respect to q, and this is q dot. So this is basically delta q by delta t. This we have already done many times. And then q depends upon p, this p, and then we have p dot. Okay, but this q dot and p dot are basically in terms of uh, the old Hamiltonian, and this from Hamilton equations of motion we know that these two are the Hamilton equation of motion. So I am going to use this in place of q dot and p dot. This is delta h upon delta pj and delta h upon delta qj. Okay, and similarly for this this pi transformation, if I take the time derivative of this, I have p which depends upon q and p which depends upon p, and then using in place of this q dot and p dot j, I'm going to use this these Hamilton equations of motion, these Hamilton equation of motions. Okay, so on the other hand, the inverse of this equation, as I have already tell that I can have this small q is in terms of qp, a small p in terms of the new coordinate. Okay, so with this what I'm going to get is this enable us to consider this h as a function of qp. So because this you know, this h depends upon this, now my h the old h Hamiltonian depends upon the old variables hp. Okay, so if I wanted to find this this h with respect to the new variables capital P, so because h depends upon q and p, so this is h with respect to q, and then q with respect to this pi. Okay, similarly h depends upon this p, and then p, and then p with respect to this capital Pi. Okay, similarly for this capital Q, I'm going to take the partial derivative of the old Hamiltonian with respect to the new Q is going to be equation 5. So now we can compare this equation 2 and 5. I have already have equation 2 here, which was we have already calculated here. So and this is my equation number 5. So if I compare this equation, this q dot, because q dot h q dot I is going to be delta h upon delta pi. Okay, because you know this if we say that this is q dot I is delta h upon delta pi. So this is in terms of the old coordinate. Okay, this is q and p, where h depends upon q and p, and when h depends upon q and p, which is basically now my k depends upon q and p, my new Hamiltonian. So this is going to be, this q dot is going to be say this is going to be delta k upon delta p. Okay, delta pi. So because the old and new Hamiltonian has to same, so if you compare equation number 2 and equation number 5 here, so what I demand is this must be equal to q dot, this must be equal to q dot. So if I demand this must be equal to q dot, so the transformation has to be canonical, then what variables, what components are going to be same? Because if you see that I have delta h upon delta qi here and delta h upon delta qi here. Okay, so that means this component is going to be equal to negative of the whole this part is going to be delta q upon p is going to be delta q upon this, and similarly for this delta h upon delta p is here and delta h upon delta p is here. So its coefficient also, this coefficient is going to be equal to this coefficient. So if I equate these two coefficients, then my delta h upon delta pi is going to be my q dot h. This is what we want. So that if I demand this, keeping the condition that we are looking for the canonical transformation, then this gives me one condition that these partial differential must be equal in terms of the old coordinates. Okay, this is what we get the condition. Okay, this is in old coordinates and this is in new coordinates, this is in old coordinate and this is in new coordinates. So if these are equal, then my transformation is going to be canonical. In the same way, we can demand for, like we have demanded for q dot, in the same way we can demand for this p dot, because p dot we can consider from here, because you know that p dot is going to be delta h upon delta q, okay, delta qi, okay, and then capital P dot is going to be delta k upon delta q. Okay, so then we demand, as we demand for q dot, capital Q dot, we can compare these two with 6, and then we get the another two set of corresponding partial differential which has to be equal. So if these set of equations together are going to be valid, then that set of transformation is going to be the canonical transformation. So one way to check this, that your transformation which is going from the old to new coordinate or new to old coordinates. So if I try to figure out that if I have expression in terms of the old and new coordinates, then if I try to calculate these differential, and if they are validating their conditions, that so then those transformation are said to be the canonical transformation. The second thing is which is coming from it itself. For example, if we transform this qp to capital QP, the old to new coordinate canonical transformation, if this is canonical transformation, my new Hamiltonian is going to be equal to the old Hamiltonian. Okay. So what is going to happen? So when this is going to preserve, this is going to preserve with this part of the generating function. So my k and h are equal, so we get rid of this, and then what we have is pi q dot, this pi q dot, and then this capital P and capital Q dot, and then this function del f by del t. So okay, if I multiply by dt here, if I multiply by dt here, multiplied by dt here, multiplied by dt here, okay, multiplied by dt here. So what I'm going to get is, because this pi dq, because dq is what, dq is my dq by dt. So what I'm going to get is pi dq. So this is pi dq. Similarly, I'm going to get is capital Pi capital dq, and this is going to be df. Okay. So this is another condition, that this is going to be my perfect differential. So if any ways if I calculate this p dq minus capital P dq, and this is going to be the perfect differential, then my transformation is canonical. Okay. So the two conditions which we had now is, one is if I have a transformation and if I calculate this and this, if this is going to be the perfect differential, then the transformation is canonical. Or we can calculate these partial differential, these two partial differential, any out of these four, which is going to be valid there, depends upon what kind of transformation is given to you. That is, if you calculate and they are equal, then that is going to be the canonical transformation. Okay. So these are two things we had to know. Now with this concept of the canonical transformation, that I have four generating function, and then how to find that the given transformation is the canonical transformation. The another important concept is the Poisson bracket in classical physics. Okay, this is again is a fundamental mathematical operation that is going to tell you that how the two dynamical quantities, any two dynamical quantities which are going to be naturally, in case of in what we are going to do is the function of the position and the momenta, how these are going to change any physical quantity, how they are going to change with respect to the change in this position and the momenta, and that mathematical operation is known as the Poisson bracket. And this is given as that if I have two functions, f and g, that is, and depends upon q, p and t, g depends upon q, p and t variables, then how these two f and g are going to change with respect to the q and p, that is given by that change of f with respect to the q, change of g with respect to the p, change of f with respect to the p, change of g with respect to the q. And then if you sum over whatever generalized coordinate, how many number of generalized coordinate q and p is there, then that is known as your Poisson bracket, that is f comma g, and the base of this is qp. Okay, so this depends upon what is the variable here, okay, on with respect to which we are going to partially differentiate it. So this is just a mathematical operation that is going to tell you how the two dynamical quantities which are related to each other and depends upon the change in their corresponding variables. Okay, so now we are going to figure out certain properties and of this Poisson bracket, that is now let us have the time derivative of the function. So let us choose the first function f and then try to get the time derivative of this function, because f depends upon q, p and t. Okay, so if I take the total time derivative of this function, so f depends upon q, and this is my q dot, and f depends upon p, that is my p dot, and f depends upon time, that is my time component. Okay, so this is q dot and this is p dot, and this is going to be have. Now I can write this as this q dot and pi dot as using the Hamilton equation of motion, because this is h, if h depends upon this q, p and t. So then my Hamilton equations of motion are these two equations of motion, q dot and p dot is related with this. So we can put it here there in place of q dot and p dot here, and that is going to be delta h upon delta pi here, and this is going to be with negative sign because this positive then becomes negative, and then we have delta h upon delta qi, and that is the time dependent of the function f is here itself. So now this quantity is I have two variables f and h, and then the both depends upon qp and t. So if I taking the variable f with respect to q and variable h with respect to p, and then variable f with respect to p and variable with respect to q, so this is exactly the definition of the Poisson bracket. So this is going to give me the Poisson bracket of the two between two variables, that is f and the Hamiltonian h, and then this df by dt is there. So this particular expression which is here, I have written here, this is the equation of motion of the function f in terms of the Poisson bracket. So and h is the Hamiltonian of the system. So if you have Hamiltonian of the system, and if you have some function f corresponding to that Hamiltonian, then the equation of motion of that function is going to be, you can write directly, that is going to be this thing. Okay, so this we are going to use later on, that this is important, that how to write an equation of motion of any function in terms of the Poisson bracket. Okay, so this we must remember. Now if my function, this is if you remember the equation of motion, the function is, that is df by dt is it's Poisson bracket with h, and then I have this is equation of motion of the function f. So now if the function f is a constant of motion or integral of motion, then this total time derivative, this part is going to be 0, because its constant of motion, is time derivative is going to be 0. So then I have this part is going to be 0. Okay, so if the integral of motion of the function does not depend on the time explicitly, then this is this part is also going to be 0. Okay, so this is 0 and this is also 0. So what I'm going to get is the Poisson bracket of that particular function, which is a constant of motion and does not depend explicitly on time. Then its Poisson bracket with the Hamiltonian of the system is going to be 0. This is one important conclusion, is that if you have a function which is the constant of motion or integral of motion, and that it does not depend explicitly on time also, then if you take the Poisson bracket of this is going to be 0. Or if you know that the Poisson bracket of a certain function with Hamiltonian is 0, then you can say that because the Poisson bracket of this function, particular function with Hamiltonian is 0, then that function is going to be the integral of motion, and as well as it does not depend explicitly on time. Okay, that's why it's an equation of motion. Now if you remember uh, this canonical equation of motion in Hamiltonian, that is if you remember this, these canonical q dot is delta h upon delta pi, and pi is delta h upon delta qi. So we can write that in terms of the Poisson bracket also. So for in place of f, if I use qi, okay, so what you're going to get is like I have to write the equation of motion for this is, so if you put here, this is going to be dqi upon, this is going to be dq upon dt is going to be, this is qh and plus delta q y delta t. So so this is not there, okay, and this is not there. So what I'm going to get is QH. So this QH is the Poisson bracket of this particular particular Q with respect to H. Let's do what is going to be there. So the Q, partial derivative of Q with respect to Q, and partial derivative of H with respect to P, and then partial derivative of Q with respect to P and this H. Now this is going to be 0, the partial derivative of q with respect to p, because partial derivative of coordinate with respect to momenta is going to be 0. This is respect to 0, so this part is not there. What I have is delta q with q, and this the first term is surviving here, so delta hp. Now this delta qi upon delta qj is going to be you know that canonical delta, that is delta qi. Okay, let me write it here. So delta qi upon delta qj is nothing but this is delta ij. Okay, and you know that this is my canonical delta, and this is going to be 1 when I equal to j, and this is going to be 0 when I is not equal to say. So this is my canonical delta symbol operator. So because you know that when I equal to j, this becomes q upon q, so this is going to be 1, and then what is not going to be the same, that is going to be 0. So this is my delta ij, and this delta h upon delta pj. So because the sum over j, see if I put this is going to be 1 when I equal to j, so put this I equal to j, so now pj becomes pi, and then I have delta h upon delta pi is nothing but qi dot. Okay, so I can say that this is qi dot is basically delta h upon delta pi, which is in terms of the Poisson bracket is qi s dot. So in the same way, if I put f equal to p, then what I'm going to get is p with respect to q and h with respect to p, and similarly according to the definition of the Poisson bracket. Now you have this p with respect to q with respect to k is going to be 0, because p is not going to depend upon x, okay, it's going to depend upon v. So this is going to be 0 on now. So why we have left with the second term with the negative. So delta pi upon pj is going to be again delta ij, canonical delta. So if delta I equal to j, I have delta h upon delta qi is basically from the definition of the Hamilton canonical equation of motion. This is going to be this pi. So Poisson bracket of p with respect to h is pi, and Poisson bracket of q with respect to h is qi dot, and these are nothing but the Hamilton equations of motion. So if you have to write the Poisson canonical equation of motion, Hamilton canonical equation of motion in terms of Poisson bracket is going to be q, h, and Poisson bracket of p with respect to h. Okay, and then if you put h equal to h, So what you are going to get is h dot h. If you take the Poisson bracket of h with respect to h, so then this is going to be naturally 0, and this dh by dt is going to be your h dot. Okay, because what you write is dh by dt is h equation of motion is delta h by delta t. Okay, so this is going to be 0. So what you have is dh by dt is total time derivative, that is going to be the h dot. We'll continue in the next class from this place. Okay, so thank you very much. Let us meet soon to get it further for this discussion. Thank you very much.